Okay, shall we start?
Yeah.
The first thing is some very fundamental of the Fourier transform. One thing is the sampling frequency. So for if the sampling period is something like a delta t, so the sampling frequency would be, or you could say fs equal to 1 over delta t, right? And or you may say omega s equal to 2 pi fs delta. This is the sampling in the time domain. So it's like you have a signal. So this is your delta t. But if you do the discrete in the time domain, you will get also discrete in the frequency domain. Something maybe, for example, like this one. You will have not a continuous. This is f omega, and this is the delta omega. And probably this way. You will have half here, 0 here. You know that, right? Because it's a period at the fs. So you can move this one to here. So it's periodic, something like this. So how you calculate the delta omega? The delta omega? Or maybe delta equal to 2 pi delta f. So this is the kind like the total bandwidth of this Fourier transform. So by if you think this from 0 to time t, this is the total time, sampling time. So I mean, similarly, that should be 2 pi delta f should be equal 1 over the total time. So it's 2 pi over t. Suppose from 0 to t you have n plus 1. Like here you have n plus 1 points. Because there's another one from here. You mean the n time period, no, n intervals. Yeah, so that the t should be equal to n time delta t, right? Yeah, so that would be, this is the 2 pi over n delta t. If you look at your xi, you will see one thing is this one. And another thing is that he called omega next is next frequency is half of the sampling frequency is called next frequency. So the fs is 1 over delta t, right? Not here.
Fs is go 1 over t,
Right? Also, in the Fourier transform, if you have like n plus 1 point in the time domain, when you do the FFT, you get also n plus 1 here, right? So that means that your, I was checking it where. You can do it here. I can do it here. Right. Also, the delta f is equal to 1 over t. That would be 1 over n time delta t. The 1 over delta t is fs, right? This one.
Yeah.
Yeah, so that's fs over n. So you have n plus 1 point here also. With the n interval. So that's delta f equal to fs divided by n. And also you are thinking about this is in the time domain, this is in the frequency domain. So but it's not necessary to be time and frequency domain. It can be space and frequency. You remember sometime you study electromagnetic. Yeah. So you will have something like in the 2D, you have this, right? That's a 2D Fourier transform. A minus j 2, I think it's just a kx times x plus a ky times y and dx dy. Oh, I should write it here. And dx dy, right? So that's another as f and t. Another one is the k and x, or maybe y, or maybe z. This is another pair. So because the k is equal to 2 pi over lambda, right? And lambda is in the dimension of this space, right? In here. So in the x side, you probably see something like a sine kx, not a sine like omega t. But basically that's the same. This x is t, this k is omega. It's the same thing. Yeah, because I see that a lot of people misunderstand which one is a frequency, which one is time or space. If I say maybe said x is equal to something like 0 dx, maybe to something like m. So this x, you can think as t. So what's the sampling period in the Matlab? You know this notation?
Yeah.
Matlab?
Yeah,
Yeah, so from 0 and time step a dx to m.
you need to specify what is the x, right?
Yeah, so this is the delta x, right?
Yeah.
Oh, delta t. This is the sampling period. So from here you can calculate the frequency, and this is the n. This is the t. The many students just write the wrong way.
So on the assignment, what part did we miss? Like misunderstand?
Oh, a lot of people know what's the sampling frequency, but they could remember which one they write down. And ask them how what's the fs, the next frequency, and what else? Ask you to calculate how many points here to here.
Oh, okay.
Yeah, and what's the delta omega? So everyone got this right, got this wrong, got this wrong. I think they just type in the Matlab command window, and they see, oh, that's maybe like 110 points. So they said n is 100. They don't know how to calculate this n. You know this how to calculate?
No, not yet. No, not really.
Oh, it's this 0, this is m, this is t, right? And you have a delta t. So actually the m is equal to number point times this one. Right? Maybe plus 1 because there is another point from 0. This n is equal to m divided by dx plus 1, total point. Another one is it may be called uncertainty principle. You heard about this one? Uncertainty principle in the quantum mechanics. You no, you didn't study that. Yeah, I thought maybe many people know that. So it's something like if you are in the quantum in an atom, you want to find maybe the electron, where it is, and what's his speed, or maybe with the speed is related to the momentum. Maybe the position you can call it delta x. That's some resolution, and his speed maybe winning some, and momentum is delta p. So this one, the uncertainty principle is that if you want to know exactly where it is, you cannot know his speed. And if you want to know exactly what's his speed, but you cannot find where it is, something like you wanted to detect the electron, you have to use something to detect him. Maybe use a photon, but when photon hits this electron, you change it. You cannot observe this without affecting him. That's the uncertainty principle. So their product must be larger than, I think this called the Planck constant. Yeah, Planck constant, something like this one. So you cannot know them both accurately. But you might know that both not so accurately. So it's a similar thing in the frequency and the time domain. You have f time t equal to 1, right? Get the f equal to 1 over t. So if you want to know if you want a very high resolution in the time domain, you sacrifice the resolution here. Yeah, you want to know very accurate here, you sacrifice here. It's something like this one. You have from 0 to total t, total sampling. Maybe you have some waveform here. This is your delta t, and so you will have t equal to n times delta t, right? You have n plus 1 point. And this sampling frequency is 1 over delta t. In the frequency domain, you probably have let's see. So this is a half. This is the and I know that this delta f is equal to 1 over t, right? And I know delta t, I know the fs equal to 1 over delta t. So these are already fixed. So now I want a high resolution here. I decrease the delta t. Yeah. But
the number of samples can be more, right?
yeah, and let's say total time doesn't change. So the number point increase.
So n gonna be
And
n equals t.
And I know that fs increase, right? But the points, yeah. But since the total time doesn't change, so your delta f is still this one. This doesn't change at all, right? This doesn't change at all, right? So basically, you expand this one. You have more here. Maybe you decrease the delta t. Your half delta s, half fs, maybe here. But here it's the same. So you didn't increase the resolution here. But another way, it's something like you keep n doesn't change, and you increase the resolution in a time domain. So n is smaller, and so fs increase. Oh. Something like okay.
How can you decrease delta t, but you keep n is the same?
Oh, you sampling at a shorter time. You you keep n doesn't change. You decrease your delta t. Yeah, so so you only sampling this long time. So that would be your t decrease, and then your delta f equal to 1 over t. This increase, right? So this you get denser line, right? Yeah. You get more information. But this overall, this one doesn't change at all. This one is this is the Fourier transform. This is infinite resolution. That's a continuous one. So another thing. Wait a second. Yeah, so this one means you increase the resolution in the time domain, but you decrease the resolution. Also, I said wrong. So delta f increase. So you decrease the resolution here, so that you cannot have resolution in both domains. And another way, if you want to increase the resolution here, one thing that, though maybe not one thing, only thing that you increase the total time t. Total time t increase. One thing that you're sampling more time. You're sampling maybe, for example, you have the sine wave. Sine wave you can sample in 1 period, you can sample in 2 periods, you can sample in 10 periods. So you will get that's the one exercise. So the longer the sampling time, that means if the delta t doesn't change, you increase the total sampling time. That means that you have more point. But you have more point, but your fs doesn't change, right? Yeah. Your fs doesn't change. So your delta f equal to fs over n. This one reduced. So you have a higher resolution in the frequency domain. And another way is you padding 0. For example, I have a sine wave. I do not sampling more time. I just sampling 1 period, but I give many 0. So that's equal to the same thing, right? The delta t doesn't change, but the total, I cannot say the total sampling time increase, but this point increase. Yeah, but the fs doesn't change. So the point change means the increase, so your delta f will reduce. So that's another way you want to increase the resolution here. Yeah. Another thing that is about maybe called an uncertain principle between the time duration and bandwidth. You remember this one, right? We have a rectangular portion. Maybe here is the tau, the minus tau is the 1. So the duration is the 2. This is in the time domain. So what's in the frequency domain? It's a sinc function, you remember, right? It's something like this one. So here at the pi over tau. This is the 2 pi over tau. This is 0 point. And this is the minus pi over tau. This is f omega. This is omega. Right? So Now, if you increase this tau, so this will get longer, right? And this one, I mean that if the tau increase here, this pi over tau decrease, right? So you will have a yeah. You basically you shrink it, you become narrow. If this one tau go into infinity, then this one go to 0, right? That's a delta function. So this one means that basically you have a DC here, and here you will have a delta function and here. Yeah, that's it. This is the DC. Maybe you have another one, something like you have a sine wave. And this one, that means you have somewhere this hit the frequency. But it's also delta function if it's infinity long. But if you sample only 1, 2, or maybe 10 period, it means you time this one with the window function. You shrink it, right? Then here that would be the convolution of him and him. So it's not a delta function anymore. Another thing that if you shrink this one, you expand this one. In the 2D is the same. This is the 1D. In the 2D, you will see. I mean, this is the image. So all this 0, this is 1. So if you shrink this one, so here in the 2D you will have a single front, but it's a 2D. You're just rotating this one. That is symmetric everywhere. So if you shrink this one, you can see the cross section. If you shrink this one, you will expand in the frequency domain. If you this center becomes larger, this one becomes narrower. So that's the rule of thumb. If you expand in the time domain, you shrink in the frequency domain, or vice versa. Another thing is, that's also like you study digital communication. Yeah. So as that is the transmit maybe like a 0 1 0 0 1 0, something like that. Right? So you increase the data rate, right? You need more bandwidth, right? You remember, right? Okay,
bit per second.
Yeah, if I want to transmit maybe 1 meg sample per second, maybe I only need some like 100 megahertz in them. But if I want to transmit 1 gig sample per second, I need a much wider bandwidth, right? This is the same thing. If you 1 megahertz, that means this one, the duration is about 1 microsecond, right? But this one is 1 nanosecond. So this one reduces a lot. This one becomes narrower, and your spectrum become wider. And you want this, so you need more bandwidth to transmit some maybe up to here, the energy. And another thing is also mentioned here about the sampling. So for example, if I have this rectangular pulse, if I only sampling only the ones, so in maybe this is it's F, no, not even F. So your data sequence is like X. They are all 1, 1, 1, 1. So what's its Fourier transform? You have all 1.
What do you mean by that?
No, if I do the Fourier transform of x, what will it look like? This is DC, right?
Yeah.
This FFT or DFT, DFT, it's thinking about the periodic. So you give this length of a sequence. Actually, it's thinking about it's a periodic. It had a periodic period everywhere. So if you put them together, it's always 1 anywhere. Right? So this is DC. But if you are padding 0, then it's not anymore. You have 1, 1, 1, 0, 0, 0. Then this one become this one, but it's like maybe shifting toward here. So it will become something like this. This is the Fourier transform, but in the DFT, you sampling this one, right? And here, if you have more 0, many 0, then means you have many n. You have a lot of n, but your fs doesn't change, so the total bandwidth doesn't change, but you have many points, so you will see more and more points. But if you have only like 2 or 3, you may see here 1, and here another 1, here another 1, here another 1. So what you see basically is this one. But you increase the n, you might have another one here, and another one here. Then your spectrum would be look like something like this one. And you have more points. You have you make this curve smoother and smoother. That's when you have like 100, you will have almost very smooth sinc function. Okay. There's a small problem. It's about a sampling theorem. The sampling theorem said your sampling frequency should be larger 2 times the f maximum frequency of a signal. Should be larger than if you don't want any lysing, the overlap in the frequency domain. So I think in the homework 1 you did that, right? You have a signal like this one, and I ask you sampling at 30, 40, and 60 hertz. So if you, for example, if you sampling at the 2 of this one, that would be something, this f max, and this also half, and this is the fs. So you will have another period here. That's why you don't have a lot. But it's not necessary to be like this. If your input signal is not this, something like this, it's a bandpass signal. For example, maybe this is FL, this is FH. If I have a signal like this, your sampling frequency do not need to be fs do not need to be this one.
It just have to be double the bandwidth, right?
Yeah, it's just not a double. It's that's pretty complicated. So no, not totally double. For example, if I had maybe this is 1, this is the 2, I have this one, and I have -1, -2, I have here. For example, if so the bandwidth is only 1, right? You said that the FSM needed to be larger than 2 times bandwidth, right? So larger than 2. So if I want it to be 3, I can let to be 3, right? Yeah, if it's 3, that means that you shift this one from here, the 0 shifted to here. So everything you will see, this is him, and you have 4, and you have 5, so you have another one here. So this overlap, so it doesn't work. So you have to like if at this 2, fine. If this 2 it's okay.
So you make sure it doesn't.
Yeah, you just don't want them to overlap. So if it's here, you shift to here, you will have 1 here, and I think another one is here. Right? So that do not overlap. So you just want to shift this one, do not overlap with one, that's fine. So I don't derive this one, but the formula is something like this. Over n should be less than fs, should be less than 2fl over n minus 1. And this n is less than 1 and should be less than this fh over fh minus fl. So the tech is the smallest, no, the largest integer. For example, if this is 3.5, I take 3. This one. And in the project, it's I think it asks about sampling a sine wave, like sinusoidal. That's single frequency. Okay, single frequency. That means that your FL equal to FH. So that means this one is 0. So n, that means n larger than 1 but less than infinity. So this n can be any number, and if n is very, very large, so this one is yeah. We can take n equal to 1. You can take n to 1. If n is 1, this one become infinity. Oh no, I think. So you want to take this one to infinity, then this is equal to 0, right? So your sampling frequency can be any number. Or another way, if your sampling frequency fixed, and your inputs can be any frequency. That's why he asks you what happened if that k is larger than 31. Then it's something like you sampling like this way, right here. If you have a sine wave, so if your sampling frequency is large enough, then you will sampling something like this, right? Then you will see a sine wave, and you will see always somewhere, maybe the sampling the maximum. But if the sampling frequency is less than, less than the highest frequency, you sampling 1 here, And the next time you might sampling one here. Okay. And next time you will sampling maybe here, and so on, so on. So if you plot many period, it not look like a sine wave, but if you get all this one move together, maybe this one, because this one is corresponding to somewhere here, right? You have another one maybe corresponding to here, corresponding to here. But basically you have all the information. So this is undersampling. If you wiki, you can find something about this one. So for undersampling is for bandpass signal. So that one is probably tricky. A lot of people said, oh, when k is larger than 31, you will have a lysing. You see that it's not a sinusoidal wave. You think it's a noise. No, the noise must come from somewhere. You didn't add noise, then there is no noise. And also in the second one, in the filter, there are two filters, right? Yeah. In the second one, there is an error in the code. Not an error. I missed one. Yeah, I missed one code, one line of code, maybe one or two code. So I want you to catch that and fix that one. Yeah. Otherwise, if you look at your I think the original spectrum, it's like you have this one. So if this is 0, it's this one, and maybe this one. It had 4 frequency, I think, right? It has like 0.5 and 0.8, 2, and 4. So after filtered, and you design a filter, right? And you filter, maybe filter this one out, something like that. But the second one, maybe second one or the first one, the filter changed. The filter is something like this one. Something like this one. But when it plots the filtered spectrum, you plot is the same as the previous one. So that's one. I wanted to catch that one. Okay, so you have any question? No. Okay, less than 1 hour. What? Yeah, the problem. So there, for that two Fourier transform xi, I want to rework the spring break and turn in after spring break. Okay? Yeah. You're welcome.